All right, I'm gonna hold the camera up to this worksheet so that you can freeze frame that. And that's what I'll be talking about today. I'll be doing problems 55 to 71. I hope I did that well enough for people to see. Let me come here. Pull that down a little bit. All right, I hope you can see the problems we're going to attack. But before we do that, I'm gonna make a couple of closing remarks. We're coming to the end of our semester. And I want to just try to summarize a little bit what we've been trying to do in class. And talk a little bit about math in general and the future courses that you're going to be studying and how important it is that you continue to work hard this last week and a half. All right, so we started the semester by saying learning how to learn. And that's really what this course was about. Some of you have been very successful with that, and I couldn't be more pleased. And others, I shake my head and wonder sometimes why there isn't more progress. Actually, I don't wonder why. I know why, because learning how to learn has some basic principles that one must, I think, follow in order to move up the ladder in this discipline. And one is getting enough mechanical repetitions to be able to handle problems. And while doing so, having conceptual considerations as to what's going on, geometrically, numerically, graphically, analytically. And that requires, this process is a little different in terms of language, because math is a language. We started there, day one. I think I wrote log base 5 at 25 equals 2, but I didn't use symbols. I think I said, can you give me the value of the exponent that you put on top of a 5 to get a 25? We know it's a 2, something like that. And I asked for, someone to tell me what I said, and it was 5 squared equals 25. And then I said, well, that's not really what I said. I said, the value of the exponent, that's what the brain has to process, and that's language. That's symbolic language. When I'm communicating to you something. And you can't answer questions unless you know what that something is, and that's what the course has been about. On a daily basis, talking about this again repetitively. Why repetitively? Because we're trying to connect neurons here. Pathways in the brain that allow you to think mathematically. And that takes patience, and it takes thinking. Okay? And many of you have put the patience and thinking into play. And after our first 2 weeks, our first test was maybe 45 problems, and the median was somewhere around 5 or 6. Which just speaks to the fact that people weren't used to doing something called thinking. Right? But now many of you are scoring in the 50s, 60s, 70s, and mid-90s. I don't say many when I get to here, but when you stop to think about the median 5 or 6, and the median right now, I think is in the 40s. Most folks, anybody who's moving along at this pace has done some reflecting and some thinking. And I still think, even with just a week and a half, for those of you who are now going to have to cram for this test, who have not been on a consistent basis thinking about the material in front of you, it's still possible to make some real gains, but it will require you to look at something each day for 4 days in a row and to think about it. And that's your challenge. All right. And it's important that you do so, because this is an entry-level class, and mathematics builds on these foundational algorithms, y equals x squared, y equals e 2 to the x, exponential, logarithmic, square root, absolute value. We've covered them all. And why have we covered them all? Because we're seeing students with a linear mindset when it comes to every calculation they're studying. And that's why folks drop out of math, because there's no conceptual understanding. Okay, so conceptual understanding takes time. Understanding mathematics is kind of like a plant growing. You can't force it. You got to give it sunlight. You got to give it the right amount of rain, and hopefully nurture it. And and you know, you get a nice crop of plants of some kind. All right, so I'm ranting here a little bit, but I'm trying to let you know exactly what it is that you have to do to make use of the last week and a half before your last final. You know, we've had about 7 finals, you know, where everything's been asked, I'm not hiding anything, saying, you know, tell us, do you understand what you're looking at and can you work with it? So Tuesday night, this coming week, there's a math help session in this room, 7:30 to 9. You can ask me rapid fire 5. If there's some topic that you're having trouble with and you'd like me to do 5 problems like it in a row, usually that's very helpful. Happy to do that. But you must know that your next level is built upon this level, and repetition is your friend. Even making videos here, I now have a science cart, so I'm just going to move it along the board. And then I won't have one of those moments where I'm talking and the screen is looking at the floor. Okay, so this is, you know, repetition's my friend. I brought the card in. I've got this now. It's going to help me simplify things. But let's just look at the squaring process, for instance. All right. You know, when you came in here, many of you didn't know how to plot. That could be pandemic related, not being in a classroom, but plotting was an issue. Do I really want to talk about this? No, I don't think I will. I think I'm going to get back. I think I'm going to get into just doing the problems. But what I wanted to mention was that, you know, upper levels you're going to be dealing with this squaring process in a much deeper level. At a much deeper level. And you can't have an understanding of what's going on with this constantly changing relationship here of side length to area. And we're going to take a microscope to it in a couple of years. And so if you're not familiar with the foundational stuff, you're not going to understand this conversation. And so that's why you've got to put in the effort now to try to get those neurons to connect so that you can be part of the conversation. All right. I may not have said that quite the way I wanted to, but let's go and do some math. Okay, so here's a typical question looking for the ability to simplify this. And some of you have been leaving this fraction as is, and that's an elementary school gap. Got to close. 21 is 3 times 7, and 14 is 2 times 7. 7's cancel, and we get 3 halves. Okay, I'm not going to talk any more about that, but I am going to talk about x to the minus 6. An equal sign means may be written as, and there is another way to write x to the minus 6. 1 over x to the 6. It's been done in earlier videos, talked about that. I'm not going to talk about that now. That's just another way of writing that. So what does that tell me? That tells me that a negative exponent in the numerator can be expressed as a positive 1 in the denominator, and it's easier to work with positive numbers. So therefore, we're going to change that to x to the 6th here. We're going to put the x to the 6th there. And now we want to talk about division by x to the minus 9. I got to get a rag here, eraser. Okay, I've got one. All right, so let's look at dividing by x to the minus 9. And let's just keep the 3 here. 3 divided by x to the minus 9. When we said x to the minus 9 is the same thing as dividing 3 by 1 over x to the 9th. And I hope, again, we don't have another elementary school gap. But when you divide by a fraction, you multiply by the reciprocal. And what was negative in the denominator is now positive in the numerator. And so therefore I can write x to the 9th there. All right, so we talked about moving. So m to the minus 5 can be written as m to the 5, and I'm not going to move m to the 3. And now I've got all positive exponents. And so the question is, what next? Well, x to the 9 over x to the 6th is the same thing as x to the 3 times x to the 6th over x to the 6th. Okay, we don't need to multiply and divide by the same number. And we're left with x to the 3rd. So there's your rule. You're subtracting in this case. And the final answer is 3 halves x to the 3 and 8 of them, right? Okay, so I don't think I have to talk about that anymore. Let's move on, my beautiful little science cart down. Okay, so knowing what the language says, you want to figure out what do you put on top of 125 to get that answer, 1/25. So that's the question mark in this equation. Trying to find the exponent that turns this number into that. Conceptually, many of you already know the answer. That exponent is equal to, I've got to take a cube root, I got to square it, and I got to drop it into the denominator or flip it. So I got to get a cube root, I got to square it, and I got to reciprocate. So there's your answer from a conceptual standpoint. Now, many of you have not processed that to that point, to that conceptual understanding. So where do we go from here? Well, let's just call this X. And let's just say that's the number we're looking for. Okay, maybe N. Maybe I'll make it N, standing for a number that gets the job done. And so I know 125 can be written as 5 to the 3, and that's raised to some exponent, and I know 1/25 is 5 to the -2. I now have the same base. So 5 to the 3n equals 5 to the -2. There's your 3n equals -2. There's your number, minus 2/3. And that means that when I check it, I have 3 operations. I can flip it, reciprocate it, turn it upside down. I can square 125, or I can take the cube root of 125. I think the last operation probably should be the first one you do. So if I take the cube root of 125, I now have 5 to the -2, which I hope you can see is at this stage of the term 1/25. All right, so there are lots of ways to find inverses. I'm a big fan of pretending that this equals some number as an equation, because how do you solve one variable equations? Inverse operations. So if I look at how I would solve this for any number, let's do a number. 3 cube root of 2x minus 1 equals, let's put a number in here that's really nice. Let's make this number 60. That's going to be fractional. So let's just say it equals 10. What would be the first thing you would do? You'd cube it, right? You get rid of the cube root. You'd add 1, get rid of that, and then you divide by 2. And you'd have an answer. So that's how we get an inverse. And that's what this notation means. Okay, so what would I do? I would take the cube root of 2x minus 1. I'd set it to some number, but in this case, that number is going to be called x. I know I've got x's in the same position here, but this is the answer I get when I solve an equation, because that's going to be a function. So I undo cubing. I add 1. This is a new number now. I'm going to put it in brackets because that number is being doubled, which means that I want half of it. And that should be my function. And I've been asking folks for the entire semester to check your answers and still not doing that. If you check your answers, you'll find your mistake, because most of you are still writing -1 here erroneously. And I have many a time thought while I was talking and doing work here that I had a correct answer, and then I checked it and I went, oh, that was stupid. I made a mistake. So let's put a nice number in here. How about we look at something that will get us an even number? So let's look at 125. So 5, excuse me. So 5 cubed. N minus 1 of 5 is going to give us 125 minus 1, 124 divided by 2. Brain work, I think that was 62. Yep. Okay. So if this is the correct inverse, then n of 62 had better come back to 5. So let's throw 62 in there, and I think I got a mistake here. Yeah, I did, see? Here, while talking, right, I should have said +1. So I just proved my point. All right, so I gotta go back and do this again. 125 plus 1 is 126, divided by 2 is 63. So therefore, n of 63 has to come back as a 5. Let's find out if it does. So 2 times 63 is 126. Minus 1 is 125, and the cube root of 125 is 5. And I just avoided a careless mistake by verifying very quickly if I had done it properly. All right, and that's not a formal proof for an inverse. A formal proof we'll be talking about at the next level. All right, with I'm not going to talk about it right now, but the formal proof is based on your understanding what I just did here. And so at the next level, if you don't understand what I did here, you have a gap, and that just causes problems at the next level. All right, let's look at the next problem. Oh, I love this card. Look at that. All right, so square rooted. All right, so this is about the square root from 0, 0 to 17 minus 6. And I've got myself a little bit of the trajectory here. And, you know, the square root process is area, the area of a square producing the side length of that square. So that's what we're going from. So if the area of a square was 0, there wouldn't be a side length. Okay, and we don't take the square roots of negatives and graph them on the Cartesian coordinate system. So there is a domain restriction and a range restriction. And if you'll notice over here, we have a minimum. So the range of a square root function is y is greater than or equal to 0. And the domain is x is greater than or equal to 0. And that is for the function y equals the square root of x. Okay. So when do we get a minimum? When whatever's inside the radical symbol takes on the value of 0. Okay. And in this case, we are starting from 0. So I can begin by saying x minus 0 plus 0. That's the general form when we have a different coordinate. So in this case, I don't need to do that. So the first stage of the principles of conversion are based on subtraction and operational division. Those are the two things that we generally do. And I don't have to subtract 0. So the first principle of conversion is complete. The next one is operational division. So if I put a 17 in here, I get the square root of 17. And that does not take me to -6. So I operationally divide out x2 minus x1 operationally, and I get the square root of 17. And that's about 4-ish, you know. I'm really going up about 4-ish, but I really want to go down 6, not up 4-ish. That gets the up 4-ish out of the picture. That brings the down 6 in. Okay. Now I'll do another one. And this was done in the first week of classes, and it has been on 20 tests. So let's look at 5, 7. Let's go up to 1943. Okay. 5. I want it to act like a 0. It does. That gives me my minimum length of a square. And I want that to have an amount of 7 attached to it. So now 5 gets me 7, and I use subtraction. Now I'm going to drop 19 in. And I have to look at the operational change. And the operational change is the square root of 14. And the square root of 14 plus 7 does not take me to 43. So I divide that change out, and I bring in what it does take to get from 7 to 43. And that's easier to compute than y2 minus y1. How do I get from y1 to y2 is a little simpler computation. And I do believe that's 36 units. And so if I put this into Desmos, I would get this graph. And I've been asking domain and range. So I hope you can see that all of these X's make bigger squares. All right, and so where did it start? At X equals 5. And all of these X's can be used, so that's my domain. My range is all about the Y value of 7. And if I'm not mistaken, these Y values are positioned where? Bigger than or equal to 7. All right, so that wasn't on your sheet, but folks have had trouble with that. So there's one more repetitive consideration. And all I can do is tell you what it is. And you have to actually reflect upon that, think upon that. You have to take a reflective moment, and I'll help you with that right now. Put your thumb and finger on your chin. Get a little front, look at it. Think about it. Okay, let's move on. Absolute value. Very similar to the square root in that it's really about a distance. But square absolute value of X is, you know, how far is that X from 0 and how far is this X from 0? And I don't think there's any place on a number line we can't say how far it is from 0. You give me a, you know, a number like -20, I'll tell you it's 20 units from 0. You give me +30, I'll tell you it's 30 units from 0. All right, so what can I say? Not much. All right, so absolute value, Y equals X. That's the graph of Y equals X. The horizontal and the vertical are the same. Okay. And when I slap an absolute value on it, all those negative answers become positives, and we get our signature V-shaped graph. And that's when we have a positive absolute value of X. We have a negative. So it's nice to graph it quickly. There we go. It's going down. I can see the vertex 5 makes that happen, and that's a minimum. A minimum becomes a maximum when you slap it with a negative. So there you have that. And what am I trying to find? I forget what I was doing with this. I assume I'm graphing it. All right, so there's that. Do I have the sheet? Yeah, it's over here. Let me just make sure. Oh, I think it's domain and range. Oh yeah, okay, it's just the range. Okay, I don't need to do anything else. All right, from the last problem we did, if you reflected on range, I hope you know you're describing the Y values. All right, which means that you're not considering that. And so where would these Y values? Y values are a vertical ruler. All right, it sure looks like this one starts here and does not go up. All right, so what is your ruler here? Y values are less than or equal to 9. And that's why I think you often see that 9 on the other side. Do I really want to even mention that? No, I don't. I'm not going to get into that conversation. It might confuse you at this point. So let's go back to that and let's just look at the picture, the simplicity of it. This is a Y value, so are these, and they are less than 9 on both sides. All right, so that one's done. All right, I'll erase these later. Got my trusty cart. Look at that. Wow. Repetition's my friend. This is a tough problem. It was a domain problem. And domain is all about the critical X values. So I think I have 2 here, 2 and 4. And so let's just plug some numbers in and see if we can use them. Let's put 10 in. 10 minus 2, 8 plus 4 minus 10, -6. That's a problem. We can't graph that on the Cartesian coordinate system. Although I think it has relevance on that Cartesian coordinate system that we don't talk about, but maybe we will if you look at the some of the work solving quadratics that is discussed. But right now I have to say no, can't use that. Can I use the number 4? 4 minus 2 is 2. I don't have a problem with square root of 2. I actually memorize it. I know that most folks still don't know what the square root of 2 is, but I'll say it one more time. It's roughly 1.41. All right, and 4 minus, what number did I pick? I picked 4. 4 minus 4 is 0, and yes, the square root of 0 is 0. Why? Because 0 times 0 is 0. It works. So yes, I can use that. How about numbers between 2 and 4? I think 3 is appropriate to use. 3 minus 2, square root of 1. Yep, that works fine. 4 minus 3, square root of 1. Yep, that works fine. That gets me the square root of 1 plus the square root of 1, which is 2. I think, yes, I can use that. Can I use the number 2? 2 minus 2 is 0. 4 minus 2 is 2. Yes, for the same reasons we could use 4. We could use 2. And then let's try 0. Let's put a 0 in here. Oh, got a problem right off the bat. Square root of -2. That's not on the real number system. So no. I guess x's could be less than or equal to 4, greater than or equal to 2. And you might have to play that video again a couple of times, but if you do it 4 days in a row, 1 minute consideration for 4 days in a row, I'll bet you that problem makes sense to you. The only problem with it is, you got to do that. All right, distance. Well, just a Pythagorean relationship. So from x1 to x2, we have a change of 5. From y1 to y2, we have a change of 5 root 3. I asked you to memorize the square root of 3. Might as well tell you again, it's roughly 1.73. It's important to know that for your future work. I'm going to make that smaller. So this is a little bit, almost twice the size, and we're trying to find that distance. All right, so I'm going to erase this so I can have some place to work here. So what do I see? I see Pythagoras. Let's put the 5 on the inside. Let's put the 5 root 3 on the inside. I mean, the challenge here is not squaring 5. The challenge is squaring 5 root 3. And what does that become? Well, let's take a peek. What's 8 squared? 64, you know that. Let's make 8 a product. 2 times 4 squared has to equal 64. So what are the mechanics of that? Well, I think because it's in a parentheses, 2 squared is 4, and 4 squared is 16, and I do believe 4 times 16 is 64. I can see that. So if I take 5 root 3 and I square it, that tells me I square the 5, and I square the square root of 3, which is 3. Okay, well now I know 5 root 3. Let's see if I can write it here, 5 root 3. If I square it, I get something 3 times the size of this. Wow, that's hard to draw. 75. Oh, well, that's a piece of cake. That means the 2 smaller ones add up to 100. And it looks like that's 10. Yeah, so I have a 5, 10, 5 root 3, which is actually something you're going to study. You're going to look at in a unit circle, 1, 1/2, root 3 over 2, or root 3 times 1/2. Right? There's a relationship here, not drawn to scale. But that's why I picked these numbers to put something in your head, whether you realize it or not. You're going to be studying this triangle a lot in a very short period of time, 2 years from now. All right, so 2/18. 2/18. Again, many of you came in and were saying 2/18 equals 9. Well, I don't think so. I think 2 divided by 2 times 9 is actually equal to 1 over 9. Okay. Now, you're not really making this mistake often, just a few of you. But when we get to the algebra, you're making this type of mistake quite a bit. So let's figure out why. Right? And why this particular problem? Well, we've been working with this a lot. Binomial squaring. And 2/3 of you are taking the shortcut, squaring the first term, squaring the last term, and then doubling the product. The question is, did you recognize it? Not so much. Okay, but even if you didn't recognize it, I think if you're going to reduce fractions, and we had 18 here, I wrote it as 2 times 9. Why? Because multiplication and division are inverse operations. You don't have to do that. All right, so you got to be able to factor. You got to be able to write things as products. And that is equal to 5x minus 2 times 5x minus 2. And that answer is, that doesn't disappear. It becomes the number 1. All right, that fits into that one time. And now that fraction is reduced. And it doesn't hurt to check your work. All right, so let's see, what would be a friendly number here? Just the number 1. 5 times 1 is 5, minus 2 gives me a 3. 25 minus 20 is 5, plus 4 is 9. 3/9 gets me 1/3. Okay, so that is letting x equal 1 in the original problem. We now come down here and we do it in the, and I'm not getting that answer, so what did I do wrong? 5 minus 2 is 3. 25 minus 20 is 5, plus 4 is 9, which is 1/3. Okay, so 1 over 5x minus 2. 3 times 5, 15, minus 2 is 13. Where did the old guy go wrong here? 29. Oh, well, no, I wrote that. Did I copy it right? Did I make a boo-boo somewhere? 5x minus 2 times 5x minus 2. Okay, I got my chin and my thumb right on the chin. Okay, maybe you're spotting it on the video that I did something stupid. 5 times 1 is 5, minus 2 is 3. X is 1. 25 minus 20 is 5, plus 4 is 9, so that's a third. And so then I did that. Yep, minus 2 times minus 2, 4, yeah. Minus 10, minus 20. 1 over, oh. Geez, talk about needing another coffee. Yeah, 5 times 1 is 5, minus 2 is 1/3. Don't know, had a cognitive moment there. As I get older, they happen to me from time to time, and I just had one. Yep, the old brain stopped. All right, so it was the same. So I don't know, am I checking what I said while I was talking to you, but it threw me off. All right, so now we've got ourselves variables on 2 sides of an equation. We gotta get them all together. Got to get those x's together in order to isolate it. In order to make a statement like that, we got to get the x's on one side of the equation. So what do? We square. Binomial squaring gets me x squared plus 4x plus 4. Okay, for those of you who have put the time in, you know how that's done. We're going to square this side. So let me touch the original. We're squaring both sides. Okay, but we got to be careful when we do that. For instance, x equals 5. When I square that, I get 25. And then when I solve that, I get plus or minus 5. And both of those answers do not work in the original. So you got to be careful when you square. You get an extra answer sometimes. And sometimes it works, sometimes it doesn't. All right, so I now know that I square that term. And I square this one. Okay, so that's not so bad. And now I've got x squared plus 4x plus 4 is equal to 9x plus 18. I know quadratics, we want to set them to 0. So there's x squared minus 5x. Bringing that over gets me minus 14 equals 0, which gets me x minus 7 times x plus 2. Many of you are leaving it like that. It's an equation. So you should continue by saying equals 0, and therefore x could equal 7 or negative 2, but we got to check those. So let's go back to the original. There we go. There's the original. We're going to plug 7 in. 7 plus 2 is 9. 7 plus 2 is 9. The square root of 9 is 3. 3 times 3 is 9. Check on the 7. Minus 2 plus 2 is 0. Minus 2 plus 2 is 0. The square root of 0 is 0. They both work. Oh, that's nice. All right, so what was it from a conceptual standpoint? Well, x plus 2 actually is a linear function that starts at that has an x-intercept at -2. This has a minimum at -2. It probably looks something like that, where that x is 7, and this x is -2, and that's where those two graphs intersect. And that one, I needed to be just a little higher for that conversation. Okay, but let's do it again. Okay, so -2 is critical. I'll just write -2 over here, gets me 0. And -2 gets me 0 there. So there's an intersection there. This starts at -2, right? The square root of 0 is what's critical. The -2 is the critical number. So we get a minimum. It's a square root function. That's the trajectory. And x minus 2 is linear. That goes up. And that's an intersection there. And that happens at x equals 7. And what is the height at x equals 7? Height of 9. So this is the coordinate 7, 9. And if you'll notice the number, no, I don't want to say anything more than that. All right, keep it going here. All right, so trying to layer a little bit of conceptualization. I can see that I want to start with y values. I'll start with 2027. How do I get, I'm sorry, I want to start with 1957, 11 to 17. I'm starting with 1957, and I want to get to 2027, which is 70 years. So the first problem, I want to get a multiplication by 0 to get that out when I use the number 11. And I also want 1957 plus 70 times 1. That's what we've been basically doing with all of our functions, 90% of them anyway. And so the question is, how do I make 1 equal a logarithm? Well, whatever the base is, it's got to be the same. Right? For instance, log base 5 of 5. Well, I made the number 1. How do I make a 0 with a logarithm? Well, logarithms are exponents. So what's the exponent I put on top of 5 to get a 0? Oh, I said that backwards, didn't I? You see, I can't do that. There is no exponent. All right, so there's a domain restriction. This number here, which is really what goes in the parentheses of the logarithm. I'm talking about this in a way that probably not helpful. So let's backtrack and let's just write the following. Log base 5 of 1 equals what? Well, that equals 0. Okay, so how do I get a multiplication of 0? By making the parentheses equal 1. I think that's probably where I should leave that conversation, right there, so that you can try to process that. All right, so let's get started here with the logarithm. And I have an asymptote of 5, which means that I'm measuring from 5. I need numbers bigger than 5 because the parentheses has to be positive. I'm just going to leave it at that. All right, so let's use the next number. 11 minus 5 is 6. 6 divided by 6 is log 1. What is log 1? There's where the 0 comes from, regardless of the base. Right? Because you put a 0 on top of a base to get a 1. So we make the number 1. So the basic rule is log 0 gets us the asymptote. Log 1 gets us our multiplication by 0. And log base and parentheses being base gets us a multiplication times 1. And so there's a little bit of conceptual reflection that is needed. So now we use 17. 17 minus 5 is 12 divided by 6 gives me a base 2. And this equation now satisfies the data. Okay, so what it looks like is x equals 5. 11 gets us 1957. And 17 gets us 2027. And there's a little bit of help here for the numbers. That's 6 units from 5. And that's 12 units from 5. Okay, so logarithms are really X values in terms of Y. All right, let me just do one more for you. Let me graph it. Let me just see if you can take something, some random numbers. Set X equals 7. And this is the inverse of exponential growth. I'm not going to hit you with inverse of decay. Not enough time in the term to cover that for the majority of folks. So let's say we got an X value of 15, and we want to have 1900. So we're going back from amounts to time. And over here, let's make that 15, 16 units from 7. Let's make this 23, and 1900, let's go to 2005. All right, some real basic numbers. So just the mechanics, 1900 plus 105. It's a logarithm. I'll put a big L there so it doesn't confuse you with the number 105. 7, X minus 7, got to have numbers bigger than 7 or you're not on the graph. Domain restriction. Put a 15 in, you get 8. 8 divided by 8 is 1. Log 1 is 0. 0 times anything is 0. Works for that, works for that. 23. 23 minus 7 is 16. Oh, 16 divided by 8. I'll write it this way. So whatever this distance is, that's twice that distance. And that's that function. Now, it would be nice at the next level to start talking about what's going on here, the asymptotic behavior. But you can't have that conversation unless you know how to do this. So you still got a week and a half. Plenty of videos out there with practice. All right, so we're going to look at composites. Composites are absolutely essential to understand, especially when you get to the chain rule in calculus. So f of 2, the original question is f of x, but I'm going to do f of 2. So what is f of 2? It means you're dropping 2 into the f function, and that gives us f of 8. What is f of 8? You're dropping 8 into the function, and you're getting 8 cubed. Okay? So in general, what did you just do? F of x is the same as f of x. So what am I dropping in first? So I think we're looking at f of x. Yeah, that was the original question. So I'm dropping x into the f function, and it becomes x cubed. So whatever number you pick, remember we picked a 2 and it became 8. Whatever number you pick, you're cubing it. And then you're taking those numbers and dropping them into the f function. And what number are we dropping in? We're dropping in that number. And what are we going to do to it? We're going to cube it. And so that is equal to x to the 9th. And that's the composite process. This is how I believe it's going to come to you in the SATs. This is how I was writing it earlier in the term. I want to make sure you know that that way of writing it is the same as this way of writing it. Boy, I'm running out of gas. Okay, the old brain is getting tired. But let's see if we can push through this with another 5 problems. All right, so log m. This is asking the question m to what exponent will equal m to the minus 3 m squared m cubed. Well, I hope we can see that 2 of them and 1 of them can become 1 of them in the numerator. M to the minus 3 could be written as m to the positive 3 in the denominator. I see 2 more in the denominator, but reducing requires me to put the number 1 there. 1 over m squared can be written as m to the minus 2. And minus 2 to the 3 gets us our answer, negative 6. That's the exponent I have to put on top of m to get this. You might want to play that more than once. Same kind of question on the other side here, 67. Basically the same question, but in this case, we're looking for m squared to the what? Is equal to m to the 3/5 to the 1/4, which is really the 4th root of m to the 3/5. That's awkward notation. So we're just going to apply the rule, which is multiplication. So that's m to the
3/20. Therefore, 2x equals 3/20. Division by 2 is the same thing as multiplying by a half. So you might be able to see your answer more easily if I multiply this by a half. And so our answer is 3/40. Let's check our answer. Let's look at m squared to the 3/40. Well, that's 2 times 3/40, which is 3/20, which is the same thing as 1/4 times 3/5. Okay. Yep, I'm on a roll here. Will I last 3 more problems, 4 more problems? I hope so. All right, so we're going back to week 1 of the term. We got a quadratic, -3/5. If I move over to the number 3, I have moved 6 units. If I square 6 units, I should go up 36 units. But I only went up 10. Boom. All right, so bottom line. -3/5. The smallest x squared can be a 0. I want -3 to act like a 0. That gets the job done. That correlates with -5, so I've done the subtraction. Subtracting a -3 is addition of 3. And then I'm dropping in a 3 to look at the operational change. And the operational change is 36 units of change. We don't want 36 units of change. How do we get from y1 to y2? By going up 10. And that's our function. You're going to leave it like that. I'm after the conceptualization. Of course, that's equal to 5/18 x plus 3 squared minus 5. Okay. Okie dokie. Oh, I didn't copy the problem down properly. Okay, I guess I got to go back over and look at that one and find out what the fraction is. Okay. It's a 4. Then 4 rubber duck. All right. Boy, I need a chair. Okay, so bingo, bango, bongo. Okay, leave that alone. I'll make it smaller. Step 1, boom, boom, boom. Step 2, fill in the parentheses. Okay, we're getting about 10% of the folks taking this test are getting this problem right. And we want that to come up big time. Bingo, 9x minus 2 times 4, 36x minus 8. Bango, 3 times 7x minus 1 is 21x minus 3. And I am subtracting that. And that's obviously 12. Okay, most folks are not seeing the distribution of the negative. So if I had the number 8 and I wanted to subtract it, it's -8. But I could write the number 8 as 2 plus 6. And if I wanted to subtract that sum, it's going to be -8, provided I put it in parentheses with a minus sign in front of it. Because I have to subtract 2 and subtract 6. And that's where people are going wrong here. Without that parentheses, and this is a really, really important conceptual situation here that you've got to understand. Subtracting something with 2 parts, you got to subtract both parts. Put it in parentheses. So what do we have? We've got 36 minus 21, 17x minus 8 plus 3 minus 5 over 12. All right, is there a nice easy number we can use? I said let x equal 5. Why did I say 5 for this problem? No idea. Let's let x equal 1. 9 minus 2 is 7 over 3. Let x equal 1. 6 over 4. Let's just bingo, bango, bongo it. 28 minus 18 over 12. That's equal to 10/12, which is equal to 5/6. Okay, that's in the original. If I don't get 5/6 out of this, then I made another careless error, and I'll have to scratch my chin and stand here and pretend that I'm awake. And I hope that I'm not running out of battery. I am. Oh my God. Okay, so I gotta go get a charger here. I don't want to lose this video. Oh, oh no. Oh, please make a noise, Lord. Okay. Oh, I can't believe that. I've been talking that long. Ugh. Come on, come on, come on, come on, come on, come on. Oh, I hear the beep. Saved by the bell. Ah, where was I? X equals 1. 17 minus 5 is 12 divided by 12. Did I make a mistake? Oh no. Oh no. Oh, 36 minus 8. 21 minus 3, 36, 27 is 15, isn't it? Oh, oh, I caught it. I caught it. 36 minus 21, 15. Oh, geez, good thing I checked it again. Good thing I checked it. Now we put a 1 in and we get 15 minus 5 is 10/12. Yeah, that's where we were. Now it's right. Oh God, good thing I checked it. So easy to make those mistakes, especially when your brain gets tired. All righty. Last one for this section of the test. All right, I'm starting just this year to say cosine, sine, tan in that order. Because cosine is really about x's, sine is really about y's. And you know, I think most people say sine squared a plus cosine squared a equals 1. I'm changing now. I'm going to go to cosine squared a plus sine squared a equals 1. Very subtle change, but I'm going to do it. All right, so we were given y equals 4. We were given x was positive. X is positive to the right side of the y-axis. X's are negative to the left. So I know I'm on the right side. Y's are positive above the x-axis, below negative. So that's where I'm drawing in the first quadrant. Future classes, you'll be, especially in the next one, you'll be drawing those in different quadrants, building upon this concept. All right, so we got to get this x value. We can do it pretty quickly, huh? 49 minus 16, 33, square root of 33. All right, so what's the cosine? Cosine is adjacent. This is your adjacent side over the hypotenuse. This is a right triangle. So square root of 33 over 4. Sine was given. It's here's angle A attached to the origin. That's the opposite side. That's the hypotenuse. 4/7 was the sine. And the tangent is really a rise over run kind of concept. 4 over root 33. All right. All right, I'm out of wind. Toast. All right, I'm definitely a piece of toast right now. Okay, we'll do problem 72 to 93 in the next video, but I'm not making it this morning. I'll make it tomorrow. All right, and this will be uploaded on Monday.